The world is messy, it's
Hmm.
complex, it's changing, often unpredictable. If you're an intelligent agent, whether that's, a person navigating their day or an AI trying to achieve a goal, how do you even start to make sense of all that chaos
Hmm.
and figure out the best thing to do?
That really is the fundamental challenge, isn't it? When AI needs to move beyond just simple reactions and actually, well, think and act with some kind of purpose.
Yeah.
And that brings us straight to the core ideas in our sources today.
hmm
Knowledge representation, reasoning, and planning.
Absolutely. We've been digging into this stack of material. There's a study guide, a briefing doc, some related notes, and they really drill down into these foundational AI concepts.
Hmm.
They show us how these ideas are basically the bedrock for building AI systems that can operate intelligently.
So our mission in this deep dive is to unpack all that for you. We want to distill the crucial insights, how AI systems perceive, learn, represent knowledge, reason about it, and then plan actions. Give you a clear handle on this really vital area of AI.
Right, because understanding this stuff isn't just, academic.
Yeah.
These concepts explain how AI goes from being like a fancy calculator to something that can actually diagnose problems or plot complex logistics.
Or even control a spacecraft autonomously, like we'll get to.
Exactly. The intelligence you see out there in the real world, the kind that adapts and pursues goals, it fundamentally relies on these building blocks.
Okay, so let's really dive in. The journey has to start with making sense of information.
Right.
And that's where knowledge representation, KR, comes into play.
Right, KR. And the sources really hammer this home. It's much more than just storing data, not just sticking info in a database.
Not at all. It's about structuring that information in a very particular way.
A way the computer doesn't just hold it, but can actively,
Right.
understand it.
Understand it, yeah.
Yeah.
Infer new things from it, manipulate it logically. The whole goal is to give the AI something closer to, human-like reasoning capabilities.
So how does that work? What are the pieces?
Well, a KR system, fundamentally, has two main components. First, you've got the knowledge base, the KB.
The KB.
That's the repository. It holds the facts, the rules, specific information about the domain. Think of it as holding what the AI knows.
Got it. The what? So what's the other part?
That's the inference engine. This is how the AI uses that knowledge.
The how.
Exactly. It's the reasoning mechanism. It takes the information sitting in the KB and applies rules or logic to drive new conclusions or make decisions, maybe find answers that weren't explicitly spelled out.
Makes sense. But building a good one must be tough.
Oh, yeah. The sources point out it needs certain properties to actually be useful. First up, it should be acquirable.
Acquirable, meaning easy to add new knowledge.
Precisely.
Hmm.
Easy to get new information in, which is vital because the world changes, right?
Instant.
So it also needs to be modifiable. Easy to update or revise what the AI knows when new information comes along or the situation evolves.
Okay, acquirable, modifiable, what else?
And this one's crucial, I think. Understandable. Ideally, the KR system is transparent, maybe even human-readable to some degree.
Why is that so important?
Well, it builds trust, for one. If an AI makes a decision, you want to be able to see why, based on its knowledge. And it helps humans debug or improve the system if something goes wrong.
Right, you need to peek under the hood.
Exactly. And finally, inferential adequacy.
Inferential adequacy. Sounds technical.
It just means the system has to be capable of logically deriving new knowledge from what it already has. It's not just looking up stored facts, it's genuine inference, deduction.
Okay, so those properties make it usable. And why is this KR step so critical for, say, an intelligent agent?
Because it's how the agent understands context, especially in those complex, messy situations, maybe where it can't see everything, partially observable environments.
Like that space probe example.
Perfect example. It can't see everything all the time, but it can use its internal knowledge model, its KB and its inference engine, to figure out hidden states, maybe predict what will happen if it takes a certain action.
Or even diagnose a problem, like a medical AI using symptoms.
Exactly like that. Predicting disease from symptoms. It's how the agent maintains its own internal picture of reality to guide what it does next.
So it's fundamental to that whole cycle. Perceive, learn, represent the knowledge, reason, plan, then act.
You got it. KR underpins so much of that internal thinking process.
Okay, so we need KR. How do we actually do it? What are the techniques the sources talk about?
Right. There are several key ways, each with its own strengths and weaknesses, different ways for the AI to see the world, you could say.
Let's start with the really formal one, logic-based representation. Sounds like math class.
A bit. It uses formal logic, like propositional or first-order logic, to encode knowledge with real precision. No ambiguity.
Okay, so propositional logic, PL, what's that?
That's the simplest form. It deals with basic statements, propositions that are just either true or false.
Like, it is raining is true, or the sky is green is false.
Exactly. And you combine these with logical connectors, and
Heh.
D or not implies things like that.
What's it good for?
Its strength is that simplicity. The semantics are crystal clear, well understood. And inference, like using rules like modus ponens, if A implies B and A is true, then B must be true, is sound and complete within its limits.
So good for simple, definite rules, like basic business policies, maybe.
Yeah, exactly. Simple rules where things are clear-cut. But the big downside is it's not very expressive.
How so?
You can't easily talk about objects or their properties or relationships between them. You can't say general things like all birds have wings easily. It doesn't scale well to complex knowledge.
Ah, okay. So limited, what's the step up from that?
That would be first-order logic, or FOL, sometimes called predicate logic.
FOL, and how does that improve things?
It extends PL quite a bit. It introduces objects, predicates which describe properties of objects or relations between objects, and importantly, quantifiers.
Quantifiers.
Like
Yeah.
for all, the universal quantifier written all.
Yeah.
And there exists the existential quantifier.
Ah. So now you can say for all x, if x is a bird, then x has wings.
Precisely. You can represent much more complex knowledge about the world. FOL is incredibly expressive, really powerful for detailed representation and sophisticated reasoning.
Sounds great. What's the catch?
The catch is, well, it's computationally very complex. The sources mentioned it's generally undecidable.
Undecidable. That sounds bad. What does that mean practically?
It means there isn't always an algorithm that's guaranteed to tell you in a finite amount of time whether any given FOL statement is true or false based on the KB.
So the AI could just keep thinking forever and never get an answer.
Potentially, yes, for some questions. That makes pure, unrestricted FOL reasoning tricky for real-time systems. You often have to use restricted subsets or specific reasoning methods.
Okay, wow. So powerful, but computationally intense.
Very. Though it's still fundamental for domains needing that logical rigor, like verifying complex rules or maybe legal reasoning.
All right. So logic is precision, but it's heavy. What if you want something, maybe more, intuitive? The sources mention semantic networks.
Yes, semantic nets. These represent knowledge as a graph. Think nodes and links.
Okay.
The nodes are concepts or objects like bird or Tweety. And the links, or arcs, are labeled to show the relationship, like is all or has part.
So you'd have a Tweety node linked to a bird node with an is a link.
Exactly. It's very visual, great for representing taxonomies like classifying animals or maybe organizing a product catalog in a business.
And how does reasoning work there?
Often through inheritance. If Tweety is a bird and birds can't fly, you infer Tweety can't fly by following those links.
Seems straightforward. Downsides.
Well, that intuitiveness is a strength,
Hmm.
but they can sometimes be ambiguous. What exactly does a link mean? They're less expressive than FOL for complex logical statements, and the inference mechanisms can feel a bit ad hoc sometimes, not strictly formal.
Got it. Okay, next up, frames. What are these?
Frames are structured ways to represent stereotype situations or objects. Think of them like data structures, maybe templates or forms.
Forms? How so?
Each frame has slots. These are like fields representing attributes or properties, color, size, make, model, that kind of thing.
Okay.
And these slots don't just hold values. They can hold default values for when you don't know the actual value. They can have constraints, facets, saying what kind of value is allowed.
Like age must be a positive number.
Right. And they can even have attached procedures, sometimes called daemons, little bits of code that run automatically when a slot is filled or read.
Interesting. So they organize knowledge quite neatly.
Yeah, they're good for organizing knowledge about typical objects or situations. That default value feature is great for handling expectations. Inference often involves filling in the slots, maybe using defaults, or triggering those attached procedures.
Feels quite intuitive, like filling out a profile. Where might you use them?
Useful for things like customer profiles, maybe representing standard operating procedures in a business context, structured information.
What are the challenges with frames?
Well, the reasoning isn't always as systematic or formally grounded as logic, and they can be a bit rigid if a real-world situation doesn't quite fit the predefined frame.
Okay. Now, related to frames, the sources mention scripts. How are they different?
Scripts are very similar in structure to frames, but they're specifically designed for representing stereotyped sequences of events.
Ah, sequences, like going to a restaurant.
Exactly, that's the classic example. Or a doctor's visit. A script has components like entry conditions, what needs to be true to start, results, what's true after, props, objects involved, roles, people involved like customer, waiter, and then the scenes, the actual sequence of events.
So the key difference is that focus on the timeline of events.
Precisely. It's about the expected progression. Inference with scripts often involves recognizing that a current situation fits a known script.
And then you can predict what happens next, or fill in gaps.
Yes, exactly. Infer unstated events, predict the next step. They're excellent for understanding narratives, maybe summarizing stories, or handling dialogue flows in customer service where there's a common pattern.
But I guess they have the same limitation as frames.
Very much so. They're quite inflexible if things deviate from the expected sequence. Very domain-specific.
Okay. One more major KR concept, ontologies. This sounds quite grand.
It is a big concept. An ontology isn't just a representation. It's a formal, explicit specification of a shared conceptualization of a domain.
Whoa, okay, break that down. Formal, explicit conceptualization.
It means defining very precisely the concepts that exist in a particular area, say medicine or finance, or even just wine. You define the types of things, classes, their properties, the relationships between them, and the axioms or rules that hold true in that domain.
So it's like creating a definitive dictionary and rule book for a whole subject area.
That's a good way to put it. The goal is huge. Knowledge sharing, reuse, and especially interoperability.
Interoperability, meaning systems can talk to each other.
Exactly. If two different AI systems or databases or applications are built using the same ontology, they share a common vocabulary and understanding of the concepts. They can exchange information meaningfully.
And that connects to the semantic web idea.
Absolutely. Ontologies are foundational to the vision of the semantic web, making web information understandable not just to humans, but to machines. They're built using standard languages like RDF and OWL.
So incredibly powerful for integration and deep understanding.
Definitely. Very expressive, formal semantics supports complex reasoning.
But the sources must mention downsides.
Oh, yes. They are very complex and time-consuming to build and maintain. Getting experts to agree on one formal definition of a whole domain is a massive challenge. It takes serious expertise.
So high barrier to entry, but potentially huge payoff for complex domains needing integration, like healthcare data or financial regulations.
Exactly. Drug discovery, large-scale data integration, anywhere you need that shared, precise understanding.
Okay, so that's a fascinating tour of how we can represent knowledge. But just having knowledge isn't enough, right? The AI needs to use it. It needs to reason.
Precisely. Reasoning is all about deriving new information from the knowledge you already have stored in your KR system.
And the sources break this down into different types. First up was deductive reasoning.
Yes, deduction. This
Yeah.
is the classic top-down logic. You go from general rules or principles to specific conclusions.
And the key thing here is certainty, right? If the starting points are true, the conclusion must be true.
Absolutely. If your premises are true and your logical steps are valid, the conclusion is logically guaranteed.
Like our all birds have wings. Tweety is bird, therefore Tweety has wings. Example.
Perfect example. It's essential when you need that certainty, applying policies, checking compliance, formal verification tasks.
Okay, what's the opposite then? Inductive reasoning.
Right, induction goes the other way, bottom up. From specific observations or examples to forming general rules or conclusions.
And the guarantee here is different.
Very different. It's about probability or likelihood, not certainty. You see lots of specific instances, and you infer a general pattern.
Like seeing 100 white swans and concluding all swans are white, which might be wrong.
Exactly. You can't be 100% sure the 101st swan won't be black. But it's a reasonable generalization based on the evidence.
And this is huge in modern AI.
It's the absolute engine behind most machine learning. Training a model on vast amounts of data to learn patterns is fundamentally inductive reasoning. Market research, trend analysis, predictive analytics, all heavily inductive.
Okay, deduction, general to specific, certain. Induction, specific to general, probable. What was the third one? Abductive reasoning.
Abduction. This one's often described as inference to the best explanation.
Best explanation.
Yeah. You start with an observation, and you try to figure out the most plausible cause or reason why that observation occurred.
So if I see the ground is wet,
the most plausible explanation you abduce is it probably rained, or maybe someone used a sprinkler. It's a best guess, a hypothesis based on the evidence.
not guaranteed truth, but plausible.
Right, plausible, probable. It really mirrors how human experts often work. Think of a doctor diagnosing a disease from symptoms. They're making an abductive leap to the most likely underlying cause. Or a detective solving a crime.
So in business, this would be like troubleshooting, root cause analysis.
Exactly those. Figuring out why sales dropped or why a machine failed. Interpreting customer feedback. It's finding the likely story behind the data.
And complex AI probably mixes these.
Absolutely. While older AI might have focused heavily on deduction, sophisticated modern systems often need to combine deductive logic with inductive learning from data and abductive reasoning to handle uncertainty and find explanations in the real world.
Okay, so we've got knowledge represented, we've got reasoning happening. But an intelligent agent needs to do things, right? It needs to act. That brings us to planning.
Yes, planning. This is where the AI figures out a sequence of actions to achieve a goal.
So it's not just reacting, it's looking ahead.
Exactly. It's a proactive, goal-directed process. It connects the current state of the world to a desired future state through a series of steps the agent can actually perform, deciding what to do and in what order.
What do you need to define for a planning problem?
Well, the sources lay out the key components. You need the initial state, a description of the world as it is right now.
Where you're starting from.
Yep. Then you need the goal state, the desired condition or situation you want the agent to reach.
Where you want to end up.
Right. And crucially, you need the set of available actions or operators, the things the agent can actually do.
And these actions need details, I assume.
Oh, yeah. Each action needs its preconditions defined what must be true about the world before the action can be executed.
Like you can't pick up an object if you're already holding something else.
Good example. And then you need the effects, how executing the action changes the state of the world. Often represented as things that become true, add list, and things that become false, delete list.
The sources mention something called the strips assumption here.
Yeah, strips planning. It's a common simplifying assumption that an action only affects the state variables explicitly listed in its effects. Everything else in the world is assumed to stay the same. Helps keep things manageable.
Okay, so you have the start, the goal, the actions with preconditions and effects. How does the AI find the plan, the sequence?
A common way to think about it is state space search. Imagine every possible state the world could be in as a node in a giant graph.
Okay.
And the actions are the edges connecting these state nodes. If you can perform action A in state S1 and it leads to state S2, there's an edge from S1 to S2 labeled A.
So planning just becomes finding a path through this huge graph, from the initial state node to a goal state node.
Essentially, yes. You can use basic graph search algorithms like breadth first search, finds shortest plane in steps, or depth first search.
But these state spaces can be enormous, right?
Astronomical. So for anything non-trivial, you need smarter search. That's where informed search algorithms like A star come in.
How does that work?
It uses a heuristic function, basically, an educated guess to estimate how close any given state is to the goal. It prioritizes exploring paths that seem to be leading towards the goal more quickly, making the search much more efficient than blind searching.
So it uses some intelligence to guide the search. What other approaches are there?
Another classic is means-ends analysis, or MEA. This was famously used in the early AI program called the General Problem Solver, GPS.
Means-ends analysis.
Right.
Trying to reduce the difference between the current state, the means, and the goal, the end.
Exactly. It works iteratively. It looks at the difference between where it is now and where it wants to be. Then it selects an action, an operator, that seems relevant to reducing that specific difference.
Okay. What if you can't perform that action right away, if its preconditions aren't met?
Ah, that's the clever part. If the preconditions aren't met, then achieving those preconditions becomes a new sub-goal. The planner then tries to find a plan to reach a state where the original action can be applied.
So it breaks the problem down recursively. Solve sub-problems to enable solving the main problem.
Precisely. It's a very intuitive way to think about problem solving. Keep producing the main difference, and if you get stuck, create a sub-goal to unstick yourself.
These sound like solid foundations, but planning in the real world must be harder.
Oh, immensely harder. The sources definitely highlight the challenges. First, as we said, the sheer size of the search space, the number of possible states and action sequences can just explode. Combinatorial explosion.
Right.
Then there's representing complex actions and goals accurately. What if actions interfere with each other? What if goals have complex conditions? And the big one, dealing with uncertainty.
Because the real world isn't perfectly predictable.
Far from it. Actions might fail sometimes, stochastic effects. The agent might not even know the true state of the world completely, partial observability. Planning under uncertainty is a whole major field in itself.
Plus, you might not just want any plan, right? You might want the fastest or the cheapest.
Resource constraints, exactly.
Yeah.
Optimizing plans for time, fuel, cost, whatever, adds another layer of complexity.
Yet, despite all these challenges, planning is used in some pretty critical application.
Absolutely. The sources mention business applications like supply chain management, logistics, figuring out optimal routes and schedules, project management, sequencing tasks, and fundamentally in autonomous systems.
Like that NAFTA Deep Space One probe example, that sounded amazing. Why was planning so vital there?
Think about it. You've got this probe millions of miles away. The communication delay is significant, minutes or even hours. You cannot joystick it in real time from Earth.
Right, you lose contact or the delay is too long.
Exactly. So the probe had to have autonomy. It used AI planning on board to diagnose problems if they occurred, figure out how to reconfigure its systems, sequence its scientific observations, manage its thrusters, all on its own.
Wow.
Planning gave it that capability, the ability to determine a sequence of actions to achieve its mission goals, responding to its situation without needing constant step-by-step instructions from humans.
That really brings it home. These abstract ideas, KR, reasoning, planning, enabling a machine to make its own decision way out in deep space.
That's the power of it. So pulling this all together, reflecting on our sources, what's the big picture on KR, reasoning, and planning?
Well, it seems clear they're incredibly interconnected. You can't really have effective reasoning without good knowledge representation, and you need reasoning to figure out what needs planning and how to build that plan.
They really are the three pillars supporting intelligent action, enabling agents to move beyond simple reflexes to actually understand their world, make considered decisions, and act purposefully to achieve their goals.
And the sources show there isn't just one way to do it. There's this whole toolbox of techniques for KR. Different types of reasoning, various planning approaches.
Each with trade-offs, suited for different kinds of problems, different kinds of knowledge.
Yeah.
And the ongoing challenge, really, is scaling these techniques, making them robust to complexity and uncertainty so AI can handle the true, messy reality we started with.
Which leaves us with a really interesting thought to ponder, especially linking back to that ontology discussion and the semantic web idea mentioned in the sources. What if that vision becomes more real? Imagine a future where much more of the world's information, maybe across the whole internet, is structured using shared formal ontologies. Truly machine understandable knowledge.
It's a fascinating prospect.
How would that fundamentally change things? How we discover information, how we use it? Could the internet itself become one vast interconnected knowledge base that AIs and maybe eventually even we could reason over in completely new ways? What would that look like?